Hi, welcome back. So in this video, I'm finally going to start talking about weather routing. Weather routing is a lot of fun, and it's also extremely useful for sailors. Uh, this video is going to be a pretty quick overview of the entire system, and I'll come back to all these topics in more detail as this video series progresses. So the general idea with weather routing is that you have a vessel uh, somewhere in the world and you want to travel somewhere else. And what weather routing can do is give you an easy way, or it's a way of helping you understand weather systems and how you can travel through them. And I'll go through several examples. In this first example, the vessel is going to be a Transpac 52, which is a fast boat, uh, which is really well suited for downwind travel. So the performance, the polar performance of this vessel, it is decently upwind. We're seeing 8 and 9 knots upwind, beam reaching. It reaches 10 knots really easily, and goes up to like 15 or so. And then downwind, in the downwind area, it just starts to scream. We're getting up to like 25 knots when the true wind is 35 knots on the behind you. So it's a fast race boat. The program comes with a wide set of polar diagrams, these performance diagrams built in, and you can import your own very easily. So the general idea is that I'm going to start this route in Nia Bay. Way up here where the start point is at some particular time, and at this point there's a green line in the grid timeline which shows the start time, and I want to go to Hawaii. So watching this weather system progress, if you wanted to stop the video and watch this animation playthrough, you could try and think about what you would do. What's the path that you would follow to go from Nia Bay to Hawaii? And if you don't want to go through the exercise, keep on watching. Now's a chance. Okay, so I'll just stop the animation briefly and I'll have the system solve this for me. So there's the path the system came up with, starting in Nia Bay, and it's traveling through the weather. It as and I'll go through in more detail how the system operates, and it's using an isochronal solution for the weather routing problem, which appears to be the most advanced. Isochronal systems seem to be the preferred way of solving this problem. And the solutions that LuckGrib is generating are, well, they're world class. They're excellent solutions. And I'll go through comparisons to some other systems in a later video as well. So very quickly, we were able to set up this problem and have the system present this route to us. I'll go through a few of these areas. So at the beginning of this route, the winds are forward of the beam, and I've asked, in this example, I've told the system to avoid wind speeds greater than 30 knots, true. So there are some winds south down here, which are stronger than 30 knots, and it's not going down there. As we progress, we hit an area here where the first tack is, and you can see that at this point the winds are forward. They're forward, pretty far forward, but the winds are veering quickly here. So if you look at the wind barb field at this point, now they're kind of south-southeast, and as the time continues, they've just gone to be south and then south-southwest and southwest and west eventually. So if this vessel had kept going forward, it would have ended up sailing straight into the wind, which is clearly impossible. So this first tack is to accommodate the veer in the wind direction. So yeah, I did that all automatically. There are some area down here where there's yellow dots. The yellow dots indicate that there's a violation of the maximum wind speed. So at this point to the east, the winds, the true winds are greater than 30 knots, and it's avoiding that area. And basically all of these tacks and jibes will go through here. you can go through and understand why it's making these choices. At this point, it's just tacked again, and here's interesting. If we go north, the winds are very light. Looks like it's like 2.5 knots of wind down there. There is an area down south of us where the winds are also very light, but there's kind of a band in the middle where the winds are moderate, or the maximum in this area. The best winds are right here where the router has chosen to sail. At this point, the winds south of us look light, but by the time we get down there, they're starting to fill in. And it just tacked again, and now the winds are improving on our beam. And I think from here on, this passage was pretty good. Oh, no, there's some light wind here as well. Tacks again to bring the wind more forward. And then now the winds are on a beam, and so on. So a quick way of looking at this, if you've watched the earlier videos, you are familiar with the idea of meteograms, which were used as a way of quickly seeing a weather system at a point through time. There's a similar idea in a weather routing system, these analysis images, which quickly show you the weather speeds at each point in the solution over the entire route. So, and there's a color legend to the left here. And we can see that initially the wind speeds are all in this green area, which ranges from around 12 knots to 21 knots. There's an orange area in the middle where wind speeds increase. Here's the deep red where the violations of wind speed were hit. And then here's the blue, the light wind area to the north and south of the route at this point. And again, we hit some more blue later on, then we do a tack. And then from that point on, we have a little bit of yellow, some increasing speeds, and greens, and so on. That's true wind speed, but of course, apparent wind speeds also interesting, as those are the wind speeds we experience on a boat. So here's a map with the apparent wind speed. And as these routes are all upwind, the apparent wind speed, it will increase. And as we go downwind, the apparent wind will decrease. So these have gone from a higher color, a higher wind. Here's the greens indicating higher true wind speed, but the apparent wind speed is clearly less as we're going downwind now. Another way of looking at this upwind downwind is with this color map, where we can look at the true wind speed as we go upwind downwind. So in this case, these deep blues indicate the wind is behind us. The apparent wind is behind at the stern. The middle greens here are at the beam, and the reds and the yellows and oranges are towards the bow. So generally the green regions are reaching, more or less. So this is showing that the initial part of the journey is more upwind, the middle is a little bit mixed, and then we head from this point on, pretty much it's all downwind. And again, you can look at the apparent upwind downwind speed. And as this boat travels very quickly downwind, what were deep downwind angles earlier have now become reaching angles as the apparent wind speed is closer to the beam. So these analysis images are quick ways of seeing the route that's generated. I think LuckGrib may be unique in showing these images, or it's definitely unique in showing them so easily. I'll also look at this day-night image, which shows you the sunrises and sunsets. So the general idea is that there's a lot of analysis tools. I'll show you one more. There's some text. So for this path, there's some statistics on the right-hand side here in this area. So this is showing that this path generated is 8 days and 9 hours long for 2,590 nautical miles. There are some maximum, minimum vessel speeds and wind speeds. This has 4 tacks, 10 jibes. And if you want even more detail, there's a text report which can be generated, which shows all the settings used in the solver. It shows the mixture of percent of time spent at different wind angles. And then for all the points along the route, it shows you some information. There's a tack, here's sunrise at a certain time, sunset. So I'll come back to this route. It's an interesting one. and I'll end up making at least two videos on this one with some comparisons to other systems, and I'll spend more time going through the weather routing techniques as well. So in this example, I'm gonna use a cruising boat which has a high performance. It's a fast cruising boat, but not a racer. This cruising boat has maximum speed of around just over 8 knots, with a fairly uniform performance. It's good upwind and downwind. But you can quickly have the system again solve this case. So here's a route it quickly generated, starting at Nia Bay, heading over to San Francisco, actually Drake's Bay, just north of San Francisco. And again, you can go through and see where the vessel is, and go through all of the tacks and jibes and see what's going on. A useful way of looking at this again is looking at the true wind speeds. So the wind speeds initially are in the oranges and yellows, which is very moderate. And there's an area over here where the wind speed is greatly increasing. So it's interesting. This is going to be, the solution for this currently is 3 days, 20 hours. So it is a multiple day trip. And it's interesting to look at where the day and night separators are. So it's starting at nighttime, and it's generally moving offshore. At this point, this is 70 miles offshore, which is pretty comfortable. And then it's coming inshore to find the optimum route. And at nighttime, it ends up being quite close to shore, tacking or jobbing back and forth. So that's going to be a lot of work. You'll have the crew getting up in the middle of the night and jibing the boat. And also you're very close to shore in this high wind speed area, which may not be optimum for a cruiser comfort. And being lazy is a virtue. So we can quickly have the system stay further offshore by turning on this extra land clearance distance, which I've set to 50 nautical miles. So we'll solve this system again. And now the route generally heads offshore. So earlier it was staying 70 miles offshore, and now the peak distance offshore is around 115. Which is fine. And it's coming into shore at night here, and it's doing a lot of tacking and jibing. So this second, we start at night. The second night has one jibe. The third night is pretty much a straight run. And we do some jibing next day, and then the following night there's a 1, 2, 3, 4 jibes, which is a bit of work. So again, we can go through and have the system start to penalize tacks and jibes. So I want to reduce how many jibes I'm doing. And I'll also turn on this nighttime penalty, tack jibe penalty, and make it larger than the daytime. So I want to have the crew do less work at night. So in this case, this second night now, it had one jibe earlier, and now there's no jibes. The jibe is around sunrise. And then the next day, we're doing a bunch of jibes back and forth. That's okay. Keep the crew busy. And then the following night, there's a one jibe in the middle, so that we can continue on to our destination. So that's really useful. You can quickly shape your route by using the weather routing settings to do what you want. If you're a racer, you probably wouldn't do this stuff. You would go in as close to shore as you need to in order to optimize your trip time, of course. But as a cruiser, you have different priorities. So that's really useful. In this weather routing example, I'm going to show a route between London and this area to the east, so to the west around Cardiff. This example works in LuckGrib just with all the default settings. Many weather routing systems have a lot of difficulty with this route. So again, I've already downloaded some weather data. This is a fast cruising boat. So yeah, let's solve this. I'm running this on a 2017 iPad, which is So it's not a super high-end machine, but the system is extremely high performance. So there's the route it generated in, well, very quickly. This takes 3 days, 9.8 hours, and it's 547 nautical miles. The big point with this one is that the route from London to Cardiff, if you go a straight line, it goes across land, and the weather router was able to realize that it needs to go backwards. It needs to go to the east first, and then around land, and then back towards the destination. Many systems find that difficult. So this first solution is only looking at the wind, but of course in this area tides are very important, and LuckGrib has a number of ocean current models. So earlier I downloaded the Copernicus ocean current data for this area. So I'll go through and I'll open up the settings. I'll have the router include current data and solve it again. So it was 3 days, 9.8 hours. And now it's 3 days, 8.5. And if I look at the current data as I look through time, I'll just close this window. And close that window. And now as I zoom in and change time, I can see the vessel leaving with adverse currents. And at this point, the current's on the beam pretty much. And then they become favorable. So things are speeding up now. And yeah, you can go through the route and see that very quickly. Now, all of the things we saw on the Mac, that's kind of interesting. It's ferrying, the boat is being pushed to the east, but heading west. So the angle between the boat heading and the boat's course is clearly divergent in that area. So sorry, I got a little sidetracked there. It's fun to watch that stuff. So I just turned on the ocean currents there. And as I know the system, I know how it works as I wrote it. I knew how to do that quickly. If you are new to the system, there's help available. In this weather routing pane, the button on the top is called routing.luckgrib.com, which is the website online. And when you push that button, it opens up a browser for you to show you all the content of the online manual and getting started guide and introduction. And when the first time you do this, it offers to have you download all of that data onto your device. And now if I was offshore with no Wi-Fi, I'm still able to look at this manual and go through and learn the system as I'm sailing. If you're leaving on a long passage, you may you'll do a combination of both those things. You'll be learning as you go as well as hopefully learning before you leave. This version of the site is easily searchable. So I can type in the search field current, done, and it finds all of the pages in this manual which are related to ocean currents. Here's one getting started with ocean currents and waves, which looks interesting. Dismiss that. And now I see that setting I modified earlier to include ocean currents is described on this page, which was found easily using this online or the web search. The feature of searching the website on your device, which you can also do offshore. In this example, I'm going to show one of the new features available in LuckGrib, which was just recently introduced in April of 2021, which makes this application absolutely unique in the industry. I think there's a general consensus that isochronal weather routing solutions are superior to other techniques, and that is the solution that LuckGrib uses. And one problem with isochronal weather systems or weather routing systems is that it's been difficult in the past to solve for constraints. I think the general consensus was that they couldn't be used. You couldn't use isochronal solutions to solve for constraints. So the example I'll use to highlight this is the fastnet race. So the fastnet leaves this area just north of the Isle of Wight, and heads over to the Fastnet Rock, turns around there, and comes back to Cherbourg, right there. Now, to start this demonstration, I'll remove the target point and have the solver simply solve the entire solution space. So it just solved to find the fastest route to any point in this whole group file, in this whole solution space, given that start time. And the point I'll make here is that all of these isochrones are non-overlapping. It's found the fastest route to any of these points from the start point and start time. But there's no way in an isochronal weather routing solver, aside from the one in LuckGrib, to have these isochrones overlap and go back on themselves. So I'll just put the target point back. So if I wanted to start in north of the Isle of Wight to do the Fastnet race, it starts here at the start point, goes to Cherbourg, and if I solve this route, then yeah, the solver's been very clever. It sees that the optimum way to solve this route is to go straight from the Isle of Wight to Cherbourg. The only problem with that is that we violated the race rules and we haven't gone around the Fastnet route. So I've created a constraint. So this is the new part in the most recent update of LuckGrib. So LuckGrib has now become a constraint-based isochronal weather routing solver, which is the first in the industry. So this green point, labeled P1, is a constraint that I've created, and I can modify this solution to respect that constraint by opening up the settings, go to the constraint sequence, specify constraint sequence 1, and now when I solve this route, the route respects the constraints that I've specified, and it starts just north of the Isle of Wight and heads out. Let's close that window. Goes around the rock and comes back to Cherbourg to finish the race. So a constraint-based isochronal weather routing system is unique to LuckGrib. It's absolutely useful and necessary to describe a lot of routes in the world, both races as well as longer routes, which you may do on the open ocean where you have a preference for some kind of a strategic goal you have in mind. LuckGrib is the only system which can do this, and I'll talk about this in much greater detail in future videos. Coming back to the Mac one last time, I'll go through one more example. In this example, I've downloaded the GFS ensemble model, and I want to travel from San Diego down to Cabo San Lucas. And I just want to demonstrate that in LuckGrib, LuckGrib is able to study probabilities and uncertainty in weather models in a wide variety of ways, including in a weather router. So in this GFS model, the GFS ensemble model, I downloaded 30 wind members, and in that space of time I was just speaking, the system generated all 30 solutions. So now if I look in the table of results, I have 30 different possible routes for this passage, given this ensemble of 30 different wind members. So in this suite of solutions, I can sort them all by duration, and the fastest route is this one, which takes 4 days, 22 hours. The longest route is 5 days, 13 hours. So that gives you a sense of the minimum maximum time that it may take to take this passage. You wouldn't expect to have either of these solutions, but it's showing you a range of the possibilities. The true winds range from 15 knots up to a maximum of 20 knots, which is very reasonable. So if I was considering leaving on this passage, I can quickly see that there's a wide range of possibilities, but the true winds are all in a very good range. In here somewhere is the control, sort of the mean. The mean is the average of all the 30 members, and the average is 5 days, 3.8 hours, with the maximum true wind speed of 17 and the maximum apparent wind speed of 11. So, and there's other ways to view uncertainty as well. There's other models you can use. There's the National Blended Models Oceanic with probability winds, and you can also analyze these things in different ways. So I've hoped that I've sparked your interest. LuckGrib Weather Routing is a world-class weather routing solution for sailors. Very easy to use, and it's very high performance, and its accuracy is comparable to anything on the market. So yeah, there's more videos to come. Thanks for watching. Bye.